Okay. So what we did, we talk about chapter 6. So I just recall. After this, we start talking about multidimensional combustion. We start talk about corrugated flame. We start talking about how flame corrugates and accelerates. And here you should remember, you may remember the following. So chapter 7. Chapter 7, oh, it's wrong chapter, I open here, no. Chapter 7 was about combustion instabilities. Basics of combustion instability. So what you may need to remember here, because many basic concepts come from the theory of combustion instabilities. So what you may remember? You may remember about idea about the following about the real Landau instability, about Landau limit. So basically is the following. So I recall if you compare slides that you see here, and third slide we see zero flame thickness, and second slide we see corrugated flame thickness. And why it's important and why is this important? And so it's very simple, because you know what? Because really, when a flame has a finite thickness, it's harder to corrugate it. Let's compare blanket and pillow. It's very easy to pack blanket, to corrugate blanket, but it's if it's like this, if it's like surface area, but it's much harder, I would say, right? Isn't it? It's much harder to deal with something. I think something goes wrong. Okay. So you see me, light if flame is planar, it's very easy to deal with a blanket like this, but it's much harder to deal something which is corrugated, which is so thick, to corrugate something thicker. So that's it is. And okay, let me share. I think I don't share screen now, right? Do I share screen? No. Okay. So here what we see. Basically here what we see, and we should realize that whenever I have corrugated flame, the larger the flame thickness, the more stable it will be. And it's physically and mathematically, so we come to it. So, and you may realize that why instability is important. So for a while it was assumed that it is turbulence which is a major role of flame propagation, but even instability, even laminar flame may be corrugated. So you may have laminar environment, no vorticity, but flame will be corrugated, steady but corrugated. And basically this is idea. So what is the basic idea about the real Landau instability? So if you consider flame and corrugated, so basically what the real Landau theory states, that if you combine all these equations ahead and behind the flame, you will come to so-called dispersion relation. And here it will be acceleration rate proportional to wave number. So basically what we call it flame sheet limit or Landau limit, what it says for us? It says for us very simple, that sigma is proportional to k. If you look at this coefficient, it's always positive. So otherwise it's like this. So if there is no flame thickness, you will see that flame shape change like this when sigma, well, generally sigma is a complex value, but here you may see that it's proportional to wave number, proportional to planar flame speed, proportional to some coefficient, which is function of theta. And what is this coefficient? This coefficient grows with theta, because I recall, if there was no thermal expansion, there would be no instability. Fluid mechanics, the real Landau, it's hydrodynamic instability. If there was no thermal expansion, hydrodynamics would not see your flame front at all. So it's corrugated here. So according to the real Landau theory, any flame is unstable, absolutely unstable. It will grow forever. But in practice, we know that it is not the case. And to explain this, people employ finite flame thickness. Because in reality, flame has finite thickness. Graphically, it's like this. So if you corrugate a flame and this arrows show heat transfer, definitely concave part will slow down, will accelerate, convex slow down. So this will moderate flame acceleration. So remember, that is how we come to it. So your expression for sigma will be like this. And you may realize that in practice, well, in first order approximation, if you don't have In first order approximation, where I can have annotation here. Yeah. So basically, what can I do? Let me do some kind of drawing here. Okay. Basically, if there is, let's see, if there is no this storm on the screen, then I will come back to the previous formula I had. But now the storm slows down flame acceleration. It can moderate it. So it happens that there is a concept of the real and Dow cutoff scale. So, and if your length scale, what does it mean for us? That all wavelengths larger than lambda critical, this threshold value grow exponentially like it was. But all small wavelengths, all small waves will be thermally suppressed. They will be thermally suppressed, and that it is. That it is. So that it is. Okay? Do you understand this? I hope so. Now, basically, that's why. And this, the real and Dow cutoff scale, lambda cutoff, is proportional to flame thickness with some coefficient which is about 1 to orders of magnitude. So that's why actually the real and Dow cutoff scale can be sometimes called effective flame thickness. Why it's effective flame thickness? What's effective flame thickness? Why I call it effective flame thickness? It's not a flame thickness, it's big. It's really larger than any flame thickness. But this is a larger scale at which you must remember about internal flame structure. On larger scales, you may say, okay, flame has zero thickness, is discontinuity surface. On scales like lambda critical or about, you should remember what is inside the flame, because lambda critical is proportional to LF. If LF is 0, lambda critical will be 0. That's what you may remember. You may remember nonlinear stabilization, and eventually you may remember this one. You may remember that this is how flame may look like. So this is corrugated but steady flame. So this flame propagates steadily with a constant speed in laminar environment, but it's not planar, it's corrugated. It's because of the real and Dow instability. And if you have larger scales, what may happen? You may remember that there are expanding flames. Flame accelerate. It may accelerate like AT to the power alpha. It may propagate, and that it is, AT to the power alpha. And basically, that's how typical corrugated flames are described. And we came back to this in chapter 10. So here are the basics. Here are what you really may remember about instability. And also what you may remember about instability is that instability is better developed on large scales, of course. But if you increase pressure, it's you may see these pictures that it's from Princeton experiments. You may see that you have different corrugated flames, different expanding flames here, and some of them are corrugated and sometimes not. And why? And there are two answers. One answer here that some of them are it's because of Lewis number. Because when Lewis number is small, we have development of thermal diffusion instability. We have imbalance between thermal and mass diffusion, like you may see here. But another point that we have different pressures here. Here is 20 atmospheres and here is 5 atmospheres. And here, remember, I showed you many times this, and I want to show you again this classical thing that we have. This setup in Leeds in UK with 1 atmosphere, and this setup, and so this is big size. It's like your classroom, right? Here are people, and this is a setup at which we see expanding flames, like on this plot. And here, this experimental setup in Princeton, when size is really small. What you have here, you have really small scale. You have just what do you have here? You just have this like an optical table, no more than optical table, and in this optical table, you have nothing but the size of this chamber. So this is your optical table. And in this optical table, you see exactly the same. So in this chamber, which is like this size, like room scale, you see exactly the same corrugated flames as you see it on big size. Why is like this? Very simple. It's like this. Why it's like this? Very because here and here we have exactly the same Dariel and Dow scale. So here you have high pressure. It's 60 atmospheres. It's 60 atmospheres, and at 60 atmospheres, what does it mean that you have 60 atmospheres? What does it mean you have high pressure? It will mean that you reduce size of your mean-free path, right? What does it mean they have high pressure? It means that you have close interaction between particles, close interaction between particles. Higher pressure means that particles go closer, you have less mean-free path, you have less transport scales, stronger transport properties, and it will mean actually that flame thickness, LF, will be less. So the real and Dow's cutoff wavelengths also will go down, it will be less. And everything will be rescaled. So on large scales, you will have the same picture before as on small scales now. You will have just rescaling. Key point that when you measure flame speed, flame acceleration, flame thickness, it should be scaled by something. In our case, it is scaled by the real and Dow cutoff scale or the flame thickness. Does it make sense for you? Do you understand this? Okay. So that it is. And also remember that in addition to the real and Dow instability, we considered other instabilities like Rayleigh-Taylor diffusion ensemble. And I show you this movie in astrophysics, how Rayleigh-Taylor instability works. And what we see is that in central gravitational field, in fact, what we have, instead of expanding surface, you have like discontinuity, so you have like sine 8. You have something like this. Yep. Does it make sense for you? Okay. Okay. Any question about at this point? Any question? Now, okay, that was chapter 7. And basically, like I told you, very often many people in combustion community, in our community, don't really merit instability much. Why? So I stop sharing screen now. Okay, so let me share it again then. Okay, so, and basically, why people don't consider instability serious sometime, which is wrong statement. Because flame corrugation due to instability, flame acceleration due to instability is typically not too strong. But why it is important to account? I will explain a couple of things. One thing, instability does not exist itself. Very often instability is coupled to what? Instability is coupled to other features like turbulence, like wall friction, like acoustics. And that's what we deal in chapter 8. That flame acoustic resonance, flame acoustic interaction may be extremely, extremely strong. It's important to remember. So if you neglect combustion instability, you will never find this feature like flame acoustic coupling, while it's important. Second, now people deal with large radii simulations to simulate real devices. They say that large radii simulations is a good predictable tool. But what is large radii simulation? In large radii simulations, people consider large scales and don't resolve small scales. They model small scales. So assume you have a model which does not resolve small scale. What does it mean? It will mean that this model most likely, as of now, neglects combustion instability, which is on small scale. So your LES will show some result, but when you will do experiment, you will have blowout, you will have explosion, you will have crash of your setup. Because in reality, instability is there and you misled it because you did not model it properly. Right? That's why instability is important. And so we always talk about high and higher pressures, and that's what the last slide I showed before. I told you that the higher pressure you have, the smaller the Landau-Daria scale is, and the stronger the effect of instability will be, because you rescale everything. Now we talk about CO2 supercritical turbine. We talk about supercritical combustion. Believe me, supercritical combustion, it is most important to deal with it. It's most important to proceed. Correct? So that it is. That it is, and that's why instability is important. And what we did in chapter 8, remember, we consider flame acoustic coupling. I don't request you to remember everything in deep details, but I request you to remember that flame acoustic resonance, it's maybe extremely strong, like it shows in this movies that I showed you when flame propagate to the wall, flame pushes the flow to the wall, it goes back, and flame acoustic coupling provides you extremely strong acoustic resonance. That it is. And basically we discussed that there are two ways how acoustic may interact with instability. One thing, resonance thing, that acoustic may actually kill instability, which is good for us. But on the other hand, acoustics generate parametric instability, they trigger secondary instability. So your strategy here is to come between stable and unstable domain, to couple between these two lines. That is something important. So I would request you to remember just these things, okay? That was acoustic. And then in chapter 9, what we did, we deal with turbulence, with turbulent combustion. So again, so this is really important section. So if you ask me, so what sections to learn, I recall definitely lecture 4, definitely lecture 6. Presumably, I do recommend lecture 7, but key point is lecture 9, turbulent combustion. And again, I cannot expect you to know deeply turbulent combustion after this, but I expect you to know at least something from here. Does it make sense for you? Turbulent combustion. And I recall you that turbulence itself, some of you is taking my turbulent class, so some of you remember, the turbulence itself, it's a very difficult topic. There is no basic theory of turbulence for reacting flows. So it's hard to deal with it. And that is why turbulence has been and still is quite obstacle for combustion. So people say that if I don't know turbulence, if I cannot describe turbulence, how can I describe combustion if I cannot describe turbulence? Luckily, and that's what we did in chapter from 10 to 15, there are many cases when you can get rid of turbulence, when you can have laminar flame propagation and when you can describe it. But still turbulence is there, you should remember about turbulence. So what you should remember about turbulence? Again, you should remember about different ways how turbulence interact with instability. I recall approach to combustion. So basically, what you may remember, what you should probably remember. So key point, what I would recommend you that for a long time, all theories of turbulence were limited to the case when thermal expansion is 1, when there is no difference between flame and the flow. Why? Because this is the case when, this is easy, because that is the case when you have basic turbulence theory, when density is not considered. It's easy. And basically this is the case when you can employ some kind of theory. Why? Because in that case, flame interacts with the flow. So what happens, we have just kinematical effect. Because there is like a flame and there is like a flow set of vortices. So your vortex take a flame and elongate it. That's kinematic drift. And that's what people employ. But what happened in practice? In practice, theta is not like the one, it's big. So flame also influences the flow. Flame is corrugated. So flame produces some new flow, and this new flow corrugates the flame. And flame also gets corrugated and generates a new flow. So there is very complex flame-flow interaction in reality. Second, since you have thermal expansion, and since your real feature of turbulence is three-dimensional, remember, especially if you take my turbulence class, turbulence is intrinsically 3D. So basically, you have many vortices in all directions. So you have vortex like this, like this, like this. So in addition to this kinematic effect, kinematic drift, you have dynamic effect that is burning along the vortex axis when it's propagating flame, and that's how it is. And what would happen? What happened? That this effect is actually stronger than this one. That you may remember. Also, regarding sources of turbulence. And basically, if you talk, for instance, any kind of, here is example of an engine, but for turbine, for any combustor, any internal combustion enclosure, you will have the same feature. So what you should account for? You have some kind of injection, right? So it generates turbulence. Also, you typically have some kind of piston which moves up and down. It generates turbulence. And also flame propagation generates turbulence. So they're together and they're interacting. That's something you should remember. Now, there is something that I do want you to remember for a final exam. That's important, really important. That is turbulent regime diagram. So what here and here. So what is turbulent regime diagram? It shows how flame interacts with turbulence in different manners. So how we plot this turbulent regime diagram? So first of all, you remember that this is logarithmic scale. It's the 10, 100, 1000, 101, and this here, right? So please remember that, and here these lines show difference between these regimes. Again, please remember what we say here. These lines are plotted by means of order of magnitude. Because everything, when we deal with turbulence, everything is order of magnitude, remember? So in fact, if I say that this is ringed flamelets and this is propagated flamelets and they differ when U prime is SL, it means that by order of magnitude. If U prime is 2SL or if U prime is 05SL, it's still the same. We talk about order of magnitude difference. Is it like 10 or 0.1? Do you understand this? I believe so. So what do we plot here? Here we plot L0 over LL. So what exactly it means for us? Here we plot integral scale, turbulent integral scale. It's characteristic size of turbulence, characteristic size of turbulent vortices. You may remember if you take turbulence class, if not, it's okay. That characteristic size, it's typically, it's chamber size, if you domain size. And this is flame thickness. And what we plot here is U prime, which is turbulent root mean square velocity. It's a measure of turbulent intensity scaled by planar flame speed. Why we do it like this? Because like what are basic characteristics of turbulence? It's integral length scale and root mean square velocity. Well, also there is Kolmogorov scale, other scales, but these are two main features, correct? What is a characteristic feature of combustion? It's planar flame speed and flame thickness. So definitely based on ratio of these characteristic velocity scales and characteristic length scales, you will come to idea how they interact. And that's what we have. Now, why I plot U0 prime here? Because that's what we measure. Remember, it's sampling effect. Because when turbulence interact with the flow, what you measure and what flame feels is different because flame also influences the flow. So here I talk about imposed turbulence, which will eventually be modified by flame. So remember this diagram. Let's go again. I can spend several minutes on this to recall what you have here. So what you have here, at the left in the corner, you have as left bottom corner, you will have laminar flames. Because what does it mean that you're here? It means here or here, what does it mean for you? It means that Reynolds number is small. You have small scales, you have small velocity, so there is no turbulence here. And now we will go here horizontally and then counterclockwise. So what is here? This is something that we call wrinkled flamelet regime. So what is it? Here your scales are big. Scales are big already. But your root mean square velocity is less than planar flame speed. So it means that your turbulence cannot change flame reasonably because flame propagates. So that's why we call it wrinkled flamelets. It's wrinkled flamelets. We call it wrinkled flamelets because, or sometimes people call it in some diagrams, you will see they call it laminar flamelets. Why laminar flamelets? They call it laminar flamelets because flame remains laminar here. Even you propagate in a turbulent flow, flame is not corrugated. Flame is like laminar. And if you go back, you may see here how it looks like. It's just laminar regime. Now, what happens here? What happens here? Let me see. What happens if you go counterclockwise? So what if you penetrate the zone what we call corrugated flame, when U prime is equal to SL and more? Here there is effect of turbulence on the flow. Now U prime exceeds the cell. So what does it mean? The turbulent velocity exceeds flame velocity. What does it mean for us? It means that it gets corrugated. It means that now you have corrugated flamelet. If you look at picture here, it means that now you are somewhere here. So compare plot A and plot B. What plot A is? Plot A is wrinkled flamelet. What is it? It means that flame is slightly corrugated, but not much. Turbulence does not change it really much. That's why you may wave it. There is no, your flame is not really turbulent. In the corrugated flamelet regime, you have strong effect. So it's like this. You see vortex is quite strong, and it's already, and actually vortex here and here is the same because you have the same length scale, right? If you just go up. but your vortex is quite strong, so basically flame is really corrugated. You may see it's not planar. You may see that this effect is conceptual. You agree? This effect is really conceptual. So, what does it mean for us? It means that here flame is corrugated, but at the same time in corrugated flame that your vortices, you see here this line, this inclined line says that your Kolmogorov scale is equal to flame thickness. So it means that up to this point, your Kolmogorov scale exceeds flame thickness. Your Kolmogorov flame exceeds flame thickness. What is it? It means, very simple, it means that your vortices, all your vortices is larger than the flame thickness. None of this vortex penetrates the flame. So it means that here we are lucky. We can describe the flame based on just geometrical consideration. So internal flame structure does not change. Internal flame structure remains laminar. But it is corrugated. For comparison, I can say like this. Imagine you are in train or in airplane, and it is big storm outside, but you sit inside. The storm shaked your plane, right? So you feel it, but this storm does not crash the roof of your plane, so you are not affected yourself. You sit inside, your internal structure in the plane, your chair, your walls, your vision remains like it was before. Internal structure of the plane is not destroyed, okay? But the plane is shaken by the environment. The same story here. So for corrugated flamelet, flame is corrugated, flame is influenced by turbulence, but it's corrugated effect, while laminar flux structure remains the same. So SL is still the same, flame thickness is the same. Transport properties are not affected by turbulence. And so corrugated flame velocity can be really described like to be proportional to the flame surface area. But if you proceed here next, and corrugated flamelet regime is what we typically have for gasoline engines, for car engines, for some gas turbines. So it's quite popular, it has practical application, it's a nice regime. But if you can keep going counterclockwise, what will happen? Your turbulence will be stronger, stronger, stronger. What does it mean stronger turbulence? It means the spectrum of vortices grows. So it will mean that your Kolmogorov scale will actually go down. And in some way, we come to the case when Kolmogorov scale will be less than flame thickness. So here Kolmogorov scale is less than flame thickness, but still Kolmogorov scale is larger than active reaction zone. So you're here. So what does it mean for us? It means that turbulence already penetrates transport properties, but does not penetrate chemistry. And if you look here, it will be as follows. So look at picture C. So now what is a flame? Flame is the distance between this dashed line and solid line, right? That is the distance. That's what you have now. Now, that is what you have. And what can I say here also? Okay, basically, what this actually solid line mean? This solid line mean active reaction zone. And what is difference between picture C from picture A and B? In picture A and B, there is nothing inside the flame. Vortices did not penetrate flame. Now they do. So what you have here? You have big vortex and you have small vortex, just for illustration. So big vortices behave like before, like they don't penetrate flame, they corrugate flame as a whole. It's a geometrical effect. But there are small vortices which are inside, and what they do? They actually modify flame structure, because remember, if somebody took my turbulence class, there is like a classical eddy viscosity model. So now you have turbulent induced transport properties, turbulence induced diffusion, turbulent induced viscosity, and turbulence induced thermal flame thickness. Flame thickness will be thickened, will be modified because small vortices came in. Like for the same analogy, if you take a train or plane in storm, now imagine the storm crashed the window, and now you have everything is crashed inside your plane, and now you are really affected by rain and by everything. Now internal structure of the plane is affected. So you are here. Of course, this requires more sophisticated consideration, and sometimes we call it still a thickened flame because it gets thicker. Sometimes we call it reaction sheet limit, reaction sheet regime. Why it's reaction sheet? It means that reaction is still of zero thickness. Reaction is not affected. Turbulence still larger than reaction thickness. But what happens if I make turbulence even more stronger? It will mean for us that eventually I have more and more vortices, they go to smaller scales, that my Kolmogorov scale will eventually less than reaction zone. So my turbulence now penetrates active reaction zone. My turbulence penetrates chemistry. And that's what we call well-starred reactor regime. Because what will happen? It will happen that imagine my vortex took one chemical radical, we move out, which influence reaction. Or I can take two different radicals from different sizes and I will have effective mixing. So my chemical mixing goes together with turbulence now. And then when we call it well-starred reactor, it will mean actually that here there is no flame front at all. Here you have mixture of fuel mixture, burnt matter, everything is really meshed, and still there are some blames of reaction, some spots of the reaction. For comparison, like imagine you cook some kind of soup. So here you have just original water and you put some ingredients. Let's say put some potato, something inside. Here you start cooking, so it's just there is some boiling, so this ingredients some jumping. But here still you will distinguish them. But while you come here, you will have like mash soup. When potatoes is mixed with carrots, with everything, and you just have one porridge, something together. That it is. So that's what you need to remember. I do request you to remember. And please also remember that the stronger the turbulence here, potentially, what does it mean? Your U prime here we show you cannot exceed actually 100 or 1,000. Why? Because then it will be not turbulence. And I taught this in my combustion class. So if you are, for two reasons. One reason, if you prime, it's actually intrinsically now I have consultation for my turbulence class as well. You know, if you prime becomes supersonic, what would it mean? What is sound speed? The speed with which information penetrates in the system. So if your fluctuations are supersonic, definitely information in the media propagates faster than the media can adjust it. And this is not turbulence anymore because this is not collective motion. Because imagine if like one piece of one locus of your system is shocked, another system don't know about this. Definitely it's not collective motion, it's not turbulence. And mathematically you can explain it as follows. And what does it mean if you go here? It means that your Kolmogorov scale will tend to zero. And not to zero, but it actually, the stronger the intensity, the less the Kolmogorov scale is. And eventually Kolmogorov scale will be less than mean free path, and it will mean that the vortices should be less than mean free path, which really violate continuum, which may never happen. So please realize. Okay, about turbulence, so that's what I want you to remember. I want you to remember this diagram. I want you to remember everything about this. I want you to remember this diagram, how it looks like. And also what we did after this, there were really different ways how to describe flame propagation. I don't need you to remember everything, but please remember that there is a renormalization analysis, which is a nice approach when we split vortices in bands in turbulence spectrum. You consider them separately and you can integrate. That's a really nice approach, renormalization analysis. That it is, well, that's what you need to remember about turbulence. Please learn it. What else? Yeah, after this, we consider other chapters. Remember, so it was chapter 10, and then, so what I recall, chapter 7, 8, and 9 gives you basic of corrugated flame. So if chapter from 4 to 6, chapter 4 was zero-dimensional flame, chapter 6 was one-dimensional flame, chapter 7 to 9 was multi-dimensional flame. We investigated instability, acoustic, and turbulence. And later, we consider some examples we employed. So what was chapter 10? It was we investigate in chapter 10, we investigated expanding flames, just particular approaches to expanding flames. What we did, we see how we can accelerate, and first we consider just expanding flames, then we investigate how acoustics can be coupled here, then we investigate how turbulence can be coupled here, and it shows that with turbulence the effect becomes extremely strong. The flame may accelerate like t to the power 4. It's a really strong effect. And also we considered central gravitational field and investigated it. Then after this, we start talking about flaming pipes, flaming domains when we have big aspect ratio. It can be slit, it can be pipe, it can be anything. And why it's important? Because it is the configuration when we may have flame transition to detonation. I recall, yeah, so what we can do, I recall Yes, these pictures that, in fact, in many slides I showed you, that's my classification for 4 fundamental configurations. That we can see the jet, we can see the confinement, we can see the open space, and we can see the eventually tubes, channels, or gaps, or tunnels. And why it's and you know why I classify it like this? It's not classical classification. It's not like premix to diffusion. It's not like deflagration detonation. But here I classify by mechanism, by reason why flame is corrugated. And here in the left-hand side, we have all friction and obstacles, which provide even really faster acceleration. And it was motivated, he shows us examples of experiments in flaming pipe or in a gap, when really flame accelerates and detonates. You saw how it goes. Why it happens here? Because you have enough time to corrugate and detonate here. It's because your aspect ratio, you have one dimension which is much larger than other dimension. That's how we did. So that's what we investigated. I remember we considered three mechanisms of flame acceleration. So-called finger flame acceleration mechanism, right? It happened at the original stage of combustion when flame accelerates. Then you can see the, we can see, again, I don't have time to teach the entire lecture again, but you can see the finger flame acceleration. It happens at the regional stage of burning. Flame accelerates here. First, it goes hemispherically, so it's not accelerating, but then acceleration starts and it goes until flame skirt touch the wall. This is quite fast acceleration, but it's limited in time. Also, we can see the acceleration due to wall friction. Here is quite simple idea, this so-called shotgun mechanism, and we have positive feedback between the flame and the flow. So let's say I have a flame and I have wall friction. So what wall friction does? Wall friction means that when flame generates new flow, it will be corrugated. So if walls are asleep, my flame will generate flow and flow will be pushed. But now flow is not uniform. We have maximal velocity at the axis and zero at the walls. So what does it mean? That your flow will corrugate the flame. Flame becomes corrugated like this. But this flame is also corrugated, so it will accelerate and corrugate the flow. And so altogether you will have positive feedback between the flame and the flow like this. It's very simple model, it does not account for turbulence, it does not account for instability, but it lets your flame to accelerate. So we discussed it, and there is one also mechanism. There is mechanism of due to when we build obstacles, because this wall friction mechanism we investigate how it goes, and we have several stages here. We have acceleration, slow down of acceleration, transition, saturation to so-called steady regime of Cherepanov-Jouguet, deflagration. Remember, Cherepanov-Jouguet deflagration is a fast supersonic regime. So basically, it's supersonic in a laboratory reference frame. So what you see propagates supersonically, but it's subsonic with respect to fuel. So still this is a flame. And eventually you have detonation. It detonates ahead of the flame. That's what we have. That's how it is. Please take a look. And what is interesting is that explosion eventually happens at the walls. Well, you have my lecture when I describe everything in more details. It's just briefly recall. It's how it looks like. And what is curious here that, in fact, in the walls, you have no velocity, no flow, but it is friction on the walls which may detonate. On this picture, detonation is red color, while green color corresponds to a flame. And by that, you may see how flame propagates, how explosion spreads, and shock waves are formed, how it goes, and how detonation happens. So key point here is what? Key point is that it may detonate, but you need a long time for this. So basically here you have finger flames, which is slow, which is fast but limited in time, and wall friction, which is slow but unlimited. And to combine them, we managed to build obstacles. And well, obstacles are known for a while because definitely obstacle-based flow is corrugated, but what we also realized? We realized that if you put obstacles like this, if you have the configuration like this, in this configuration, we have flame propagation through obstacles, it may be corrugated and accelerate. And so here, turbulence plays a supplementary role, and mechanism itself is very strong. So I recall you, this is what we call Bychkov mechanism, or toothbrush mechanism, or comb shape mechanism. Idea is quite simple. So basically we have obstacles, and these obstacles actually cover your walls, so they prevent finger flame acceleration to stop. They somehow isolate your flame from walls for some time. So we have these pockets. And what happens in these pockets? You have flow, flame generates a flow, but because of this obstacle, this flow cannot go here. So flow goes backward, and we generate a jet flow which is propagating, and that's very huge effect. And in fact, it's enough to have aspect ratios about 15, 20, 30 to detonate. And here you may see again, it's very similar picture that we had before, but now flame may detonate very fast. You remember the movies how it goes? That's how flame accelerate, and this is DDT due to obstacles. That's how it happens, that's how it detonates. And basically that's what we did. And so that was chapter 11 when we discussed these effects. And chapter 12, what was chapter 12? In chapter 12, we discussed basic features, how we can promote and how we can facilitate combustion in different configurations. And basically, why we need it? Because basically the idea, what we need. Basically, we considered unobstructed pipes and obstructed. So here are scenarios how it goes. So in both cases, what do we have? We actually have 4 stages. You may see we have 4 stages of acceleration. So you may see what we have. We have exponential acceleration. Then we have slowdown of slime acceleration due to compressibility, saturation to Chapman-Jouguet deflagration, and eventual explosion. The same for obstacles. Now, if I want to suppress this, like if I'm in coal mines, if I talk about fire safety issues, so I want to kill all the stages, if ever possible to do it. But if I want to use this device, like in some kind of pulse detonation engines, somehow I should promote. And I told you that my personal strategy, that instead of detonation, you might use fast deflagration. You might be here. Instead of here, you might be here. That was my personal strategy, my personal consideration. And what can we do here? Basically, the idea was that instead of using detonation, which is efficient but very dangerous, let's use deflagration. So let's keep this stage for a while. So here at this stage, you can use everything you can to suppress flame. All features to suppress it. While here you want to prolong it. And what to suppress, what to accelerate. That's what we investigated. And basically, we investigated what we can do, and we come to the following conclusions: that how to promote flame acceleration. Putting obstacles. If you put obstacles, you definitely will promote it. If you try to make flow turbulent, try to put acoustics, but acoustics may be positive or negative. Initial ignition like finger flame shape will help. You may reduce Lewis number, thereby you will promote diffusional thermal instability. And definitely you can increase thermal expansion, and also combination of these effects will work. Now, how to mitigate flame acceleration from, again, wall conditions. Actually, the left-hand side, I didn't write it down, but because if you have a diabatic pulse, it will accelerate promptly. So how to mitigate? Use open or vented ends. If you open end, if you move vent end, you split the flow between upstream and downstream, you reduce pressure abundance, you will slow down the effect. Put isothermal walls instead of adiabatic. Put heat losses to the walls. It definitely modifies the effect, but again, it depends where. Because if it's in the case of obstacles, the effect will be minor. But in the case of non-obstacles, this is tremendous effects that may change the role. And if you can reduce heat walls, here I would say it's really tremendous effect. What else? Put smooth slip walls, and they will kill wall friction. That will help you. Increase Lewis number, decrease thermal expansion. That's all will promote to mitigate. So that's what we discuss in detail. And actually, what I can do, maybe now I can actually even here I will write reduce heat losses. That is important, but why I didn't write it before? Because that actually does not work together as obstacles, either or, I would say. That's what we need. Now, that's what we did. That's mostly what you should remember. I don't want to go through chapter 12 because we'll spend 1 more hour. We're already about 2 hours here. Now, in chapter 13, what we did, in chapter 13, we employed this to particular case of mining safety. So we see how to employ what we had and how to employ different strategies. So what is our typical strategy in coal mines? I think I wrote it somewhere. Let me check here. Yeah, so basically we talk about in coal mines, definitely we want to suppress fires. So basically we want to have a condition where fire does not happen. But why fire does happen? Typically because you have methane, and also because you have coal dust impurities. Coal dust, which is very combustible, when it cooperates with methane, it becomes very explosive substance. So our strategy is just to predict the risk of particulate fire, how to avoid it. And unfortunately, our measurement devices, our sensors are not perfect. They measure concentration of methane, they measure concentration of dust, but they cannot measure it in any locus when explosion may start. So also, so what we should do? If fire starts, we analyze, and again, here I cannot help with my research with this, what we discussed in this class, because it's most likely chemical things, how to predict if flame starts or not. But if fire starts, we can do something, we can do many things. So one of the things we can say that, okay, if fire starts, how it will develop? Our strategy should be to kill flame if it starts, to terminate it, or to minimize the hazard if this is the case, so we can analyze it. If we cannot prevent flame propagation, let's at least slow down it. Try to slow down such that it will attain the fast stage as long as not soon as possible, such that people can hide or run away. Eventually, if we cannot avoid this, if we cannot avoid transition of the flame acceleration, let's avoid or at least postpone transition to detonation. Why transition to detonation? Because detonation is very dangerous in enclosed like coal mines, like subways, not just because of combustible nature, but because of waves, shock waves. Shocks propagate very fast, they can crush people, they can kill people, crush equipment on very, very long scales when you're in enclosures. So that's what we predicted, and that was the way how to employ to practical reality. We discussed how to predict all these parameters. It was one of my last lectures, lecture 13, we discussed it. And then there was idea also how to properly describe coal combustion. There is here classical C# formulations, and what you do that. Of course, in reality, it's multi-phase flow. But if you're lazy to do real multi-phase simulations, what you can do, you can introduce such an effective fluid. And in such an effective fluid, you will say that you have effective particles, effective burnt matter effect and effective fuel, and instead of considering particles, you say, let's say I have a fluid by my transfer properties are now modified because of particles. I have modified effective equivalence ratio, effective planar flame speed, effective Zeldovich number, effective other parameters, and that allows me to consider it. So that's what we employed here. That it is. And okay, in chapter 14, we talk about triple flames. Well, no, there is nothing about that's all. That's all. So what happened in chapter 14? It was one of the last lecture. Well, just I don't want to go through all chapter 14. Actually, I send you modified chapter 14 because that is enough for you to know. So we talk about very basics. We talk about triple flames here. So the idea of what I request you may remember disk law when you have operation of particles, because you may remember basic idea about diffusion flame, Borges-Schumann scenario, all this configuration for diffusion flame. You may remember that to describe diffusion flame, like premix flame, you write your equation in Z space, in mixture fraction space, not in classical space like a Fuzil-Deutsch-Frank-Kamiensky solution. And important is that even for diffusion flame, premix flame based becomes important. So what I want you to realize that, let's say I have a flow like this, I have fuel, I have oxidizer. So in fact, what is diffusion flame? It means that you have this domain when you have mixing of oxidizer and fuel and combustion happens. But also realize that before it happens, here you have effective mixing. So at some point, premixed flame segments become here, there, here. This is so-called flame base. And here, so here you have a lean premix segment, here you have rich premix segment. And point when they intersect, this so-called triple point, and this is stability point, because this point can be actually attached to the nozzle. It can be lifted far away, but it is this point which is responsible for combustion instability. And what does it mean? Even if whole energy released depends on this bulk flame structure, it is this point which shows importance, shows why it's so important to consider. That's chapter 14, and in chapter 15, what do I have in chapter 15? It was just extension of combustion science to other fields, like and again, that's what I described last time. We talk about what? We talk about supernova, because supernova combustion, it's really supernova explosion. It's really classical, both thermonuclear or gravitational. It's classical way to describe it based on DDT, deflagration detonation transition. The only point here is that instead of chemical reaction, you have nuclear reaction. Everything else is the same. Also, here you should realize what we have. We have central gravitational field, and it's important to remember this gravitational field. It happens, like I show you these movies, I believe, many times. Let me see. I think I show it to big screen. I show you these movies, how flame expands and how this infinity sign appears. Here it is. Yes, so here is how bubbles is formed, and this is for thermonuclear supernova. I stopped the door. And here, like brain-like structure, this is expanding flame in supernovas, classical simulation. And in gravitational, again, similar story happened. What is gravitational supernova? I recall you, it's when we have very, very huge mass from 8 to 40 solar masses, when eventually, like black hole, it can be formed, and then you may see this transition from deflagration to detonation, how it goes. These bubbles in gravitational supernova. You may see it here as well. That it is. So again, I gave a very basic introduction in supernova here, but just to inspire your interest to proceed in this direction if you have interest. We say again, laser ablation, when you have controlled fusion, when you want to have, like, instead of magnetic trap, laser trap, when you can irradiate target, and with laser ablation you have exactly the same like for flame. It's very good analogy when you have flame propagation. And the same story, because the only thing that here, and here it's not the same story actually, here is the case where instability is extremely important. Because for laser ablation, what we have? We have tremendously big thermal expansion, we have high Mach number, and we have tremendously big temperature dependence of conductivity, which really gives you tremendously big diffusional thermal and the real down instability, which should be counted. But if you employ combustion science here, potentially it will help you with control fusion. And we talk about organic semiconductors. Remember this front which will go, it's like in light emitting cells, like, or photodiodes. When they are when these organic semiconductors, what happens here, that instead of direct transition from dielectrics to conducting, from conducting state, here this transition happens like this. We have front of holes, front of electrons, they meet, and p-n junction starts. And key point that if you make and this really, these fronts can be described like a flame, and if you have corrugated structure of these fronts, they meet faster and they will promote the device you have. Because key point here is ion, we have ions, holes are actually ions, right? Electrons are fast, but holes are ions which have low mobility, they're heavy. And device with low mobility cannot be turned on, turned off promptly. It may take actually for organic semiconductors, it may take about a minute to turn it on, which is not good if you talk about TV set, for instance, or cell phone. So this is the way how you may accelerate it. We may corrugate it and it will propagate faster. And it really resembles flame. And again, so what you have here is so-called plasma instability, which exactly remembers the real and down instability. But instead of pressure abundance, you have electric field abundance here. And I thought the same for magnetic avalanche in crystals. How they go, that you have a front which changes like this, it's front of magnetic which propagates. Anyway, I cannot repeat all combustion class in one lecture. I already spent about 2 hours on this. So that's all I have. So please ask me more, ask me some questions. If you have, I believe you will have some questions. So please, I will stop sharing the screen, and that it is. But I believe you should be ready for combustion course. Nothing special about this. Yep. Any questions, please? Okay, if no questions, again, let me wish you all the best. So again, I will prepare separate exams for you, but with minor difference such that you work independently because your peers will have something different. I will, so your exam is on Wednesday morning, formally from 8 o'clock, but I intend you to send your assignment somewhere in the very, very morning and 7 o'clock, and please send it back to me by the end of the day. That it is. Also, yeah, please send me all you owe me so far, like paper reviews, anything. And please, yeah, if you did not evaluate this course, please evaluate it, still student evaluation before it's closed. Not everyone did it yet. Okay, thank you and good luck on Wednesday. I'm ending now. Yeah, and what I will do, okay, I will post today's review. I will post it for sure. Okay. Christian, you're most welcome. It's my job. Say thank you for coming for the review. So what I will do now, I will post this. Please evaluate this course if you did not yet. Please send me everything. I will post today's review. It will be too serious because we stopped, right? I will post it online again on YouTube, and we'll send you the link, so please you can go through it. And also on a separate email, I will again send you all my solutions to all your homeworks, quizzes, such that you will have it in your hand in one package to go through it. Okay. Okay. Thank you then, and thank you, and see you sometime. Hopefully after summer, but on Wednesday we will still see you through this link. Okay. Let me